It's surprising that only 4 chemical elements make up most of our bodies: C, O, H, and N, carbon, oxygen, hydrogen, and nitrogen. Here you see them represented as colored balls and sticks, or letters and lines. The sticks or lines indicate the valency of an atom, its ability to share electrons and form chemical bonds. Sharing electrons is like the glue that holds atoms together, forming chemical bonds. In methane, a very simple compound, carbon binds to 4 hydrogens to give CH4. The hydrogens and carbon share their electrons equally. Now let's look at water. Water is made of 2 hydrogen atoms bound to an oxygen atom. However, in contrast to methane, where hydrogen and carbon simply attract their shared electrons, oxygen is said to be markedly more electrophilic, that is to say, having a much stronger attraction for electrons than does hydrogen. This greater affinity for electrons by oxygen leads to an uneven distribution of charge within the water molecule. This makes water polar, meaning that the oxygen side of water is more negatively charged than the hydrogens. As a result, the hydrogens are left a bit more positive. The molecule as a whole, however, continues to remain electrostatically neutral. Water is a simple V-like molecule, the oxygen bound to 2 hydrogens, and is thus said to be a dipole, having 2 poles, one more negative and the other more positive. This makes water very special. You all probably know that opposite charges attract each other. Negative charge attracts positive charge. And so the oxygen of one water molecule can align with a hydrogen of a neighboring water molecule. In such a situation, the 2 molecules are weakly attracted to one another. A bond is formed through this electrostatic attraction. The oxygen for the hydrogen of its neighbor. This bond is called a hydrogen bond, which is formed between neighboring polar molecules, in this case, 2 water molecules. Hydrogen bonds are not as strong as true chemical bonds that actually share electrons. The electrostatic attraction between polar molecules is relatively weak, but nonetheless very important, and it explains a lot about how water affects and participates in the world around us. The molecules of liquid water arrange themselves, forming a lattice, a network of molecules oriented to maximize the formation of hydrogen bonds. These bonds are what hold water together. It takes heat to break the hydrogen bonds until ultimately water boils and releases water molecules as steam. Hydrogen bonds can be formed between any polar molecule, in addition to water itself. Let's go back and look at methane, CH4. In one of the valences of carbon, if one is replaced with an oxygen atom bound to hydrogen, we get a new molecule called methanol, a simple alcohol. The OH group is called a hydroxyl group, and in it the oxygen is polar and consequently can hydrogen bond by surrounding water. Adding more carbon and hydrogen groups to methanol will reduce the polar effect of its single hydroxyl group. For example, adding a CH3 group to methanol creates a different alcohol called ethanol. Actually, we're all familiar with this alcohol. As it's the alcohol in whiskey, beer, and wine. Cheers. Ethanol is polar due to the hydroxyl group, but it is less polar than water due to the extra carbons and hydrogens. This is why ethanol boils at a lower temperature, 78 degrees centigrade, and evaporates more readily than water. This is because there are few and weaker hydrogen bonds holding these molecules together. Carbon-containing molecules, organic molecules, can be more or less polar, depending on the number of polar groups they contain. More polar, the more likelihood the molecule will react with the surrounding water molecules through hydrogen bonds, and thus will be hydrophilic. that is to say, attracted to water. If a molecule does not have polar groups, then it is unable to hydrogen bond with the water. In this case, it is said to be hydrophobic, afraid of water. Hydrophilic solutions do not mix with hydrophobic liquids, and thus water does not mix well with oil. As hydroxyl groups are added to organic molecules, they become more and more hydrophilic. However, if we extend the chains of carbons and hydrogens, hydrocarbon chains, the molecule becomes more hydrophobic. Some molecules are a bit schizophrenic in that they contain both hydrophilic and hydrophobic parts. These substances are amphipathic, meaning they have both characteristics. They are both hydrophobic and hydrophilic. Soap or detergents are, for example, amphipathic.